Alright, hello everyone. Right now we're just going to be going over some tutorials on RNNs and their use and reinforcement learning. It's going to be a very open-ended tutorial. I'm going to talk about some thoughts that I have about it in general based on some papers that I've read, and just, you see ablation studies, things like that, and like you have ideas of your own of things that you'd like to do. And I'm gonna at the end I'm gonna talk about what I'm trying to do right now to see if it works. But I'm one guy and I don't have a ton of time. But we're gonna be going over the use of RNNs in reinforcement learning. So just a quick disclaimer. This code is really just about getting like all the other tutorials code walkthrough. This is about getting your environment and training set up correctly. I don't guarantee any of the models that that I show you are going to converge or anything, and I'll explain why you should not expect any of these to be like extremely optimal or anything like that. With that being said, I also want to warn you guys to make sure you guys understand all of the math before you go in, because you can spend a long time on things that you shouldn't have wasted your time with. Just a quick little, I guess, story is that for months and months and months, I kept going back to this project in TensorFlow of a continuous agent, continuous actor critic agent, and I always kept getting the same error over and over and over and over. I'd have like a discrete actor critic agent, and I try to change the code, just modify the policy so it goes to continuous distribution, and I get the same error all the time. No gradients provided, and there would be no gradients, and it always confused me what's going wrong. Why is this not working? Because I'd done it previously in Pytorch, and I would not get the same error. So it was very confusing because I'm much more comfortable with TensorFlow, only to find out just a couple weeks ago I was looking at a tutorial for soft actor critic, and I realized, as I was going through like the tutorial, that just how there's the reparameterization trick, which is used in soft actor critic, or which is used in like a variational autoencoder. They mention that when you're sampling from a normal distribution or a Gaussian distribution, that is considered a random node, and gradients cannot flow through a random node. And they explained it, and it's super obvious now. However, in TensorFlow, there are things that you have to do to account for that, because you can't just sample from a normal distribution that you get from output from your network. However, in Pytorch, they work around that, and they actually allow you to. So they kind of like include the reparameterization trick, where instead of sampling from any given distribution, you're sampling of the standard normal distribution, and then they just adjust it using the mean and variance afterward, and that allows gradients to flow through. So make sure you have an understanding of the underlying math for anything you're doing, because I didn't know that. I didn't know gradients could not flow through a random node. So I spent a long time on something that I thought was a TensorFlow error or code error, when it's really, oh, the gradients can't flow through because gradients can't flow through a random node. Anyways, let's go ahead and jump right into the code. So the code for the continuous implementation, since this is just a basic actor critic, is going to be in Pytorch, because Pytorch allows you to just sample directly from it. And so we're going to be using an agent class in this tutorial. Excuse me. We're going to be using an agent class in this tutorial. And typically in the other tutorials, you guys don't see me using an agent class. And I got this class because, how you want to set it up, that's up to you. But some of this code is copied from the Machine Learning with Phil tutorial series, and he has one on continuous actor critic using the mountain car environment, I believe. And I have some of the code copied, just which is why it's inside of an agent class. He has great tutorials. Whenever I'm confused, sometimes I look at his videos go check them out. But you guys will notice there's an agent class here, and it uses the same methods for like choosing action, and well, that's not the same method. Change the name and like a learn method. So check out his videos if I'm not clear enough. But his videos don't include the use of an RNN, which is what we're going to be learning right now. So RNN, as I'm sure you guys know, is a recurrent neural network, and it has advantages of using it with sequences instead of with individual time step samples. So let's just go ahead and jump right into the code. We're just going to be applying it to the pendulum environment from Jim. And it's the same pretty much as A2C agent, which is advantage actor critic agent. But instead of just a normal multi-layer perceptron network, we're going to use RNN network. Okay, so we have to start with our imports. Import torch as T, import torch neural network as NN, import torch.neural network.functional as F, import torch.optim as optim, import Jim, import statistics. So just normal imports. And we have to make our environment. So we're going to call gym.make with our environment name, which is pendulum-v1. And we're going to define that as our environment. So this is the most basic RNN you could literally possibly build. There are more advanced RNNs available right now, such as LSTM and GRU, GRU being the better one. It's better for training speed and also for longer sequence lengths. But we're just going to be using a basic neural network. Basic linear layer right now instead of a GRU layer. So the code we got for the neural network, for our recurrent neural network, is we go to Pytorch, we go to tutorials, and then we go to text in our tutorials, and then we go NLP from scratch, classify names with a character level RNN. And we're just going to go ahead, go down to where they're defining their neural network. So they explain exactly what a neural network is, an RNN, how it takes the previous output, feeds it back in through the hidden layer, etc., etc. So this is the code for the neural network we're going to be using. So you can go ahead and copy this and just paste it directly into your code. And we're going to be modifying, because we're not going to be using softmax. We're going to be using the actual logits for the output. But anyways, you can copy this code, but this is where I got the code from. So let's take a look at the actual defining the model of RNN. So we're defining class RNN inherits from nn.module, and we're going to initialize it. Takes self, input size, hidden layer size, and the output size and the learning rate as arguments. We're calling super RNN for the super class, so we can subclass it. And we're just defining our learning rate as self.learning rate equals learning rate, self.hidden size, and this is just from our inputs. Hidden size is hidden size. And we're going to go ahead and define the two layers that are actually going to make up the network right now. So we have a hidden state layer, and we're going to call that, so we just take a normal linear layer, neural network.layer, and the input size for it is the size of the actual input, like our state observation, plus the size of our hidden state. And we're going to go ahead and concat those in the forward pass. You'll see that. And the output is just the hidden size. And the output layer, it's just the size. It's just another normal linear layer, and it takes input size and hidden size for the input. So we add those together for the input size, and the output size is just the size of the output that we want. Okay. So we're going to be getting multiple outputs from this network, because we're going to run these in parallel. We're not passing the hidden state to the output layer from the same pass. And we have to define an optimizer. We're going to use Atom, and it's going to be optimizing the parameters for this model. So we're going to call self.parameters, and the learning rate is going to be equal to self.learning rate. So let's go ahead and now define the forward pass for this model. So the forward pass for this model, it takes the state observation, input observation, and it takes the previous hidden state, or whatever the hidden state is. If it's the 0th index, it's the hidden state you create for it. anyways, so we go ahead and we take the input and we make sure that's a tensor, because since we're going to be working with like a gym environment, it might come in as a list or an array or whatever. So we convert our input to a tensor, and then we use torch or t.cat, which is it's just going to concatenate whatever arguments we give it, and we have to define an axis for along which axis we concatenate. So we say our input and our hidden that gets passed in. We're going to concat those along the first axis, and we're going to call it combined because we're combining our input and our hidden state. Which is, so concatenating them, we're kind of just adding them together, but not the add operation. But which is why whatever length this is plus whatever length this is, we're gonna combined is gonna be that size, which is why we added those sizes together up here. Okay. So now that we have a combined input and hidden state, we're gonna pass that to our hidden state layer because it takes the combined same thing and same as the output layer. So we pass our hidden and our combined, which are just linear layers. Both of them are combined. Sorry, we pass combined to both our hidden state layer and our output layer. And we're gonna get as return our hidden state and our output, and we're gonna go ahead and return both of those values. Okay, so in case you guys don't know what a hidden state is, it's kind of just a way for, it's essentially just a memory for our network. And based on what that memory looks like at any given point in time, it kind of remembers, for example, this is just, I just came up with this off the top of my head, so maybe a very poor example. But as you're growing, your weight changes or your height changes. So if someone says, oh, what were you doing when you were 3 feet tall? You might think that was when I was 10 years old. Here's like the things the types of actions that I might have been doing when I was 10 years old or 3 feet tall. Versus when you're, when you're 140 pounds, what were you doing when you're 140 pounds? Oh, well, I must have been 16 years old. These are the types of decisions I was making if I was in this circumstance. So that's a very poor example, actually. But essentially what we're doing is we give it as a hidden, our hidden layer. We begin it at any sequence with an array of zeros. And then depending on what step it's on, it uses backpropagation to say, oh, instead of zeros, now I'm 1, 0, 1, 3, or whatever, if it's like a sequence of its hidden state of size 4, and those values are going to change. So it's kind of creating a memory, like an encoded memory, essentially. So it always begins with zeros, and as the sequence goes on, it changes. So if it goes through a certain sequence of hidden states, it knows that it's seen similar sequences. So we need to define a function init hidden, which is just gonna return a tensor of zeros, which we call t.zeros for torch.zeros, and just a single example, and the size is self.hidden size, so the size of our hidden layer. Okay, so that's our network for the RNN. Okay, that's how we define a simple, very simple, most basic RNN network that you can define. Okay, and we can query an environment to know what's the observation size and action size, what those look like. But we already know that that as an observation, our environment is going to return an array of size 3, and it will take a single action in return, and we'll go over that in a minute. So we need to know the input size, which is 3, because it receives a state of observation 3, and yeah, so number of outputs, we'll go over that in just a second. Whoops, don't like the way any of this looks, but I'm not going to restart the recording. And the number of outputs is just how many how many nodes are going to be in the output layer. Okay, so the number of outputs is how many nodes is going to be in the output layer. So this is going to be a continuous distribution. So the output layer needs to define two things for us, a mu and a sigma to define our continuous distribution, as we've gone over in the other policy tutorials. So since this only takes the action only is going to be a single value, we're only constructing one distribution. So the one distribution needs two values, a mu and a sigma. So we're just going to say number of outputs is equal to 2. And here's the code that I copied. Well, not copied. A lot of it is very, very much changed. From the Machine Learning with Phil tutorial, go ahead and check that out for Pytorch Continuous implementation. But so in here, this is just basic setup. And we're gonna need a learning rate for an actor, a learning rate for a critic. We're gonna need a gamma, like for all of them. We're gonna need number of actions. And some of this is reused. It's a little bit messy, but you guys can clean it up in your own implementation. We're gonna need to know the layer sizes of our network. So we're gonna have 2 layers in our network. So layer 1 size is 64 units, layer 2 size 64 units, and number of outputs is 2. And we're just going to redefine everything from our inputs. Self.gamma is equal to gamma. Self.logprobs is equal to nothing yet, because we're going to calculate that later. Self.advantages is equal to an empty list. And these can be defined as none and none. Okay. Do I define it or do I add it to self.logprobs and self.advantage? Okay, we set it equal, we don't append it, and okay, so that's fine. So we're setting our advantage to none, our estimate to none, our ground truth to none, entropy to none, and so we are going to use entropy. Well, we could, and I'm going to show you how to omit that if you guys would like to not use entropy in your examples. But you're going to need an entropy beta if you do, and this is probably the simplest implementation of using entropy that you can use. Your entropy beta we're not doing like reward scaling for our entropy right now, which you could in a better implementation, obviously. So we're just going to use a basic entropy beta of 0.005, 0.05, and that's just based on what the reward and entropy looks like for this environment. You might have to change it for a different environment. Anyways, so we go ahead and define our actor and our critic networks, and these have to be separate networks for the environment that we're doing, because we're running our critic and our actor at separate points in the training loop. So I have seen, and there's plenty where they're the same network, and it branches out to an actor head and a critic head, but these are just 2 separate networks. Okay, so our 2 RNNs take an input size, hidden size defined as 300, output size as number of outputs, learning rate is equal to actor learning rate. And same thing with the critic, but the critic only has a single output because it's only outputting a single estimate for the value of any given state. So the only difference is that our actor has several outputs depending on how many actions it must take, and our critic only needs to know, make an estimate for a single value, which is the value of the given state. Okay, and we're defining an actor hidden equal to none and critic hidden equal to none, and we're going to be resetting those throughout our workflow. Okay, so let's go ahead and ask it to so let's actually go to the training loop before we go and talk about choose action and run critic and learn. Okay, well actually we can do learn in a minute, but we need to talk about our training loop. So the only thing that's really different from a training loop is that we're going to have an observation trajectory for our during training. So, for normal actor critic, we might just be holding on to the single state as it is, but we're going to be needing to hold on to a trajectory of, any given length of the trajectory of the states that we've seen, because we're going to feed it as a sequence to our RNN, because our RNN works on sequences. So we're going to need an observation trajectory. We're just going to use a simple list for that. And I have a little bit of code down here just to actually keep our observation trajectory to a super short length, which is just 4 states at a time. So it's not like we can, well, I guess you could change this value right here. So change that to like 32, and now you take lengths of up to 32. But I'm just gonna put it to 8 right now, or 6 or 4 or whatever. And we're using shorter lengths because we're using the most basic implementation of an RNN. So we're gonna be dealing with the exploding and vanishing gradient problem. So we're not gonna wanna have super long sequences, which is also why our learning rate is gonna be very small, because as we add more, as our sequences get longer, that's more layers in our RNN network, and you know, the whole vanishing and exploding gradients like goes through the roof at that point. So I'm keeping the sequences short. So I'm keeping the observation trajectory to a maximum length, and then I'm resetting the observation trajectory and then adding the most recent observation to that trajectory again, so we can continue the sequence, you know, on and on and on. And so we with each step, we take our most recent state and we put it into our observation trajectory, and which is a list of states, and then we tell our agent to work with the observation trajectory, not just the most recent state. Okay, and anytime we're running some like we're running our critic or our agent, it has to take the observation trajectory, not just the most recent observation. Okay. Anyways, let's go on. So choose an action. So to choose an action, we just need our observation trajectory, and we're going to go over the last sequence of observations of length, you know, any value 1 through 6 or 1 through however long you want your observation trajectories to be. And this is just the way we implement it in Pytorch. Okay, so we're going to call agent.actorHidden, and we're going to initialize our hidden state to be all zeros. And now we're going to replace our actor hidden to be replaced with all zeros. Okay, and we take our observation trajectory, and so pretty much what we're doing at this point is so we're going to go ahead, and the way that we set up our network, we're going to actually feed it one state of our observation trajectory at a time with the hidden state. We're going to get an output, a new hidden state, and then we feed that new hidden state with the next index of our observation and our observation trajectory. So pretty much what we're doing is we have to call t.unsqueeze, and we have to make sure that our observation trajectory comes in as tensors, because it's getting it as I believe NumPy arrays or lists. Okay, so we have to, this is our new observation trajectory as x, and we have to call x.size to find out how long that observation trajectory is. And then for the length of that observation trajectory, we're going to go ahead, so for each index in the length of that observation trajectory, what we're going to do is we're going to call the forward pass on our RNN network, and we're going to feed it the ith time step and the hidden state for that from the previous time step. If it's the 0 time step, we initialize it to 0. If not, the output from the network, as we saw above, is the output and the new hidden state. So what happens is we get the output from our agent, which is mu and sigma, and we get a new hidden state, and our new hidden, so we're redefining our hidden state. So for the next pass in this loop throughout the trajectory, the new hidden state is not going to be zeros, it's going to be whatever the output for the previous hidden state was. So we have our output, and we're changing our hidden state for each time step. And then for our final time step, which is the current time step we're on, we're just going to go ahead and take the output from the network, which is mu and sigma, and we're going to index that. So the output has 2 nodes. So the first node, we're going to call it mu, and the second node, we're going to call it sigma. Okay, and so the thing is, it returns the output as a batch. So we're going to get the 0th index of that batch. Okay, so we get mu sigma, the 0th index, and the first, and then we index the first, which is sigma, which is our standard deviation, and we're going to define that as sigma, and we're going to call t dot abs on it, because this, like we've gone over before, this has to be positive. This has to be, you can't have a negative sigma, negative standard deviation. And we're defining mu as t dot tan h on the other output from the network, okay? And so now we have a mu and a sigma from the output of our network, and it's gone through a sequence of time steps, and it's given us values for current time step. So now we need to construct a distribution. So we call t.distributions.normal. We pass in the mu and the sigma as our arguments, and we get a distribution in return. And we're going to determine the entropy of that distribution very simply by calling distribution.entropy. And we're just going to set our entropy to that value, the return value, which is the measure of entropy for that distribution. And we also need a sample and action. So we're going to call distribution.sample, and we just want a single sample in return, and that's going to be our torque. And we also need to know what the log probs are for taking that selected action given that distribution. So we have to call distribution.logprob on that torque. And, you know, I called it torque 1 or whatever because, you know, whatever. And you could actually do, you know, several of these. But anyways, so we have to make sure, so our environment is actually going to take an environment for the action space. It takes upper and lower bounds for its actions. So for this environment, it takes all values between -2 and +2 for the actions. So we're just going to use tan h on the torque. So all of our values get rescaled between -1 and 1. And before we pass that to our environment to actually step the action, we're just going to multiply it by 2. So all of our actions will be between the range of -2 and +2. So we're going to go ahead and return the torque, which is going to be, thanks to this tan h, is going to be between -1 and +1. And then, you know, that's going to work in our training loop, and that action is going to get multiplied by 2 and passed to the environment, and our environment is going to give us a new state, a new observation. So let's go ahead and talk about run critic and what we need to do for run critic. So we need to actually pass into run critic quite a few things for this network, because after critic, we're trying what we're trying to optimize for our critic is it to minimize the loss, like the estimate between the ground truth value and its estimate of the ground truth value. So that's the loss we're trying to minimize for our critic value. And so the way that we actually determine the value of any given state is we determine the reward for the state that we received for the state we're in, and we add gamma times the estimate of the next state. However, that estimate of the next state, we don't want to track gradients for that because it's just an estimate. It's not really what we're expecting for it. So we actually have to run that without tracking the gradients for it, and you'll see that in just a second. So when we're when we're doing the calculation for loss of the value received in that state. Anyways, okay, let's just go through it, and hopefully it makes sense as we go through it. So we receive as input for a run critic, we receive a reward, we receive the observation trajectory, and the next state, which is after we took the action and whether or not we're done. So we take our observation trajectory, and we're going to do the exact same thing we did for our agent. So we're going to initialize our hidden state, redefine our in state, determine the length of our observation trajectory, and for each item in our observation trajectory, we're going to pass in that item into our neural network with the current hidden state, and we're going to receive back the critic value, which is an estimate of the value of that state, and the new critic hidden state, and we're going to redefine and we're going to put the new hidden state as self.critic hidden. So we can just call it in the next pass. Okay. So we're going to define self.estimate, which is the critic's estimate of the state value as critic value. And we receive our reward as just a normal like Python type. So we're going to convert that to a tensor. And so that was the estimation of the value of the current state that we took the action in. However, to actually find the value of that state, we need the reward plus the value of the next state. So now we need to do the same thing that we just did up here using all of the states including the current state, but we need to do that using all the states including the next state, which is why we have the prime state or the next state. So what we're going to do is we're going to take this prime state and add that to our observation trajectory and run it. So now it's going to be running with everything including next state. Okay. So we're going to take our observation trajectory and append our prime state. So now it's including the most recent state. And we're just going to redefine that as next state trajectory and call t.unsqueeze, t.tensor observation trajectory along the first axis. And we're going to reinitialize our critic hidden state to be all zeros. And we have to call with t.nograd. So this right here, we have to run our model on the next state within the scope of t.nograd. And the reason for that is so we're not tracking our gradient. So when we do the update step, it's as if the model doesn't even know it ran it on the observation trajectory with the next state. And the reason for that is because we don't want to optimize against that, because that's just an estimate of the next state. We don't actually have a ground truth for it, so we can't optimize against it. Okay. So we're going to find out how long that new trajectory is, which is just going to be one longer than what this one was. And for each observation in that trajectory, we're going to call self.critic.forward with each index in there plus the hidden value. In return, we get the estimate of the critic value and a new hidden state, which is going to be new self.critic hidden, and that gets passed in through the next iteration. So the ground truth value for okay, I'm a little confused right now because I read through this and I should have caught that. I'm not sure if I'm missing something, but the ground truth is supposed to be reward plus the critic value for the next state, which is critic value underscore times gamma. And I don't know why I didn't multiply it by gamma, and I don't know how I'm looking through it super quick. So I'm gonna actually add in times self.gamma right now, and yeah, because yeah, that I believe I'm correct. Self.ground truth is equal to reward plus critic value, the critic value for the next state times self.gamma. So I'm gonna keep that in there. I believe that's correct now. I think it was incorrect before. But that's what our ground truth is going to be. If you're having issues, go ahead and omit that. But I think that's the correct way. And so our advantage, since this is not a basic actor critic, this is A2C, which is just adding an advantage. And you know, in other ones, you can do things like subtract the mean reward to find out what a pseudo advantage might be. But we're just, for the great thing about actor critic is our critic is always going to be providing an estimate of what it thinks the state value should be. However, if we receive a reward that's greater than that state value, that's advantageous because that means whatever we thought we were supposed to get for a state, we received more. So that's a great action. That's not just a good action. That's a great action. So we're going to want to calculate our advantage, and our advantage is equal to our reward plus self.gamma times our critic value times 1 minus int done. And this is just something that we have for like terminal states. That way we're not actually estimating the value of the next state if we're in the terminal state, because there is actually no next state. And we subtract our actual critic value from it, So the advantage is really just taking our normal ground truth and subtracting our critic value from that ground truth. So whatever whatever we estimate the ground truth to be, we're gonna subtract our original critic value from that to determine how much advantageous any individual action was. So we're gonna call that as self.advantage. Excuse me. Self.advantages is equal to advantage, which we just calculated up here. So now let's go ahead and call self.learn. And you know, I sincerely apologize to anyone for these tutorials if you're actually watching them hoping that like you can get something out of it and I'm not providing that to you. I do sincerely apologize. I'm just trying to help you guys out, and maybe you just to help people understand the workflow in general. This is great for like workflow in general. So like I said, I do apologize. I'm trying I wouldn't say my best, but I tried my best to put the code together, but these tutorials are kind of less than optimal. Anyways, so I do apologize for that, and you know, I'm re-reviewing code that I wrote a long time ago with all this documentation that I wrote in here. Look at all these notes I wrote in here. Nothing. So I'm just going off what I remember. And after reading it a couple times. Anyways, so let's learn. So this is where we're just implementing the basic algorithm for actor critic. And you can get that anywhere, and the algorithm is just written in a million different places for actor critic or A2C. And instead of so we're gonna have a loss for actor, loss for a critic. Gonna combine those losses, do backwards propagation on them, and optimize. And that's all it is for the learning step. So for our actor loss, and all of these values that we're gonna be pulling right here, which is why I did this. I actually try to copy the code and then remove the agent class. But the agent class actually is great because all of your values are right up here waiting for you. So that makes it super convenient. And okay, so our actor loss is going to be equal to the negative of our self.logprobs times self.advantages plus, and we're going to have an entropy term in here as well. You can omit this entropy term. So like we calculated entropy earlier. You can just go ahead and omit that term if you'd like. But I added it in for exploration, and depending on your environment, your entropy beta is going to be different, or if you're doing reward scaling, it's going to be different, etc., etc., etc. And I don't think I talked about this, but the great thing about these losses is you can just go ahead and you can add, like, let's say this is exploration, even though, you know, entropy is typically used for like exploration, but you can go ahead and add as many terms as you want right here and call them whatever. You can just say plus exploration term, and however you're determining that, you can just go ahead and add that in and optimize for that as well. But we're gonna keep it for now because it kind of does help. So, and then we have our critic loss, which is gonna equal our the estimate of the value for a state minus the actual ground truth value of that state, and we're going to go ahead and square that just so we have a positive value, because we're going to do minimization on that loss. And you know, self.estimate minus self.ground truth, depending on which one was more, we might end up with a positive or negative value. We square that, or you could call t.absolute or some function to get it positive, and that's going to be equivalent to our critic loss. We add our actor loss and critic loss, call backward on it, and then we step our optimizers, and then we reset our gradients to 0. So let's go ahead and look at the training loop one last time before I hit run very quickly. So we have our agent, and we just our actor learning rate is equal to 0.001, critic learning rate is equal to 0.0001, gamma is 0.99, standard layer 1 size is 256, layer 2 size 256, and number of outputs is equal to 2. And we have a couple values up here. This is just for monitoring our metrics, which you've seen in other ones. We're just keeping track of our scores and our entropies just to see how our scores and our entropies are going throughout training. And a sample number of episodes that we're going to be training on, let's just say 500. And so for each episode, we create a new observation trajectory. We reset our score to 0, entropy to 0, done is equal to false because we've barely begun. And we add our most current state to our observation trajectory. So we're just calling environment.reset, and that resets our state. And we just pass it to our observation trajectory as a list because we receive it as an array, and we're just converting it to a list. And you may be able to omit that. It's just one of those things that's in there. You know, when you're trying to get things to work, you do all types of type conversions. Anyways, so while not done, so we're now in our loop. We're going to get our agent to choose an action. So it takes our observation trajectory and it returns an action, which is going to be between -1 and 1. However, our environment takes actions between -2 and +2. So we're going to take our torque and multiply it by 2 and call environment.step on torque times 2. And then it returns to us a new observation, a reward, a done flag, and information. And we're going to throw away that information. So we're just leaving that in an underscore. And we're going to take our agent and run a critic. So it takes as arguments a reward, the observation trajectory, the new state, which we're going to call list.onObservation, because our observation still gets returned as an NumPy array, so we're converting that to a list. So we can just append that in our updated observation trajectory and a done flag. And once we do that, just because of the workflow of the order that we changed the observation trajectory, we need to now add the new state in. So when the next pass on the new observation trajectory, it also has the new state, because inside of run critic, we're defining the observation trajectory underscore, which is different. So we need to update this actual observation trajectory, which is what we do here. We now say we've run the critic on it. Now let's append our new state. So the next action has the newest state in it. Okay, and we're gonna after we do that, we're gonna call agent.learn. Log our scores, log our entropy, and make sure our observation trajectory is not too long. Okay. And if it's too long, we're gonna reset the length and add the newest state to it. So so the observation trajectory would just be a single time step long. And this is just for monitoring scores.append score, entropies.append entropy. And we're just gonna log these every episode and take the average of the last 20 episodes using statistics.mean, and we're going to log and the episode number. And like I said, the reason why I'm keeping these observation trajectories short is because we're using the most basic RNN. I'm going to talk a little bit at the end about using different types of like the GRU layer in Torch or TensorFlow. But anyways, so I'm going to go ahead and hit run, and we're just going to see that it's running and it's training. So -886. So that was, that's what it gets off the bat. So just so you guys are aware, a normal MLP agent will probably get like 1400 on average or 1500 on average for this environment. So if you get it to do something like 1100 or 1000 and it's learned and it's reached like let's say 1000, obviously it has not solved the environment, but it shows signs of learning. And like I said, I'm making no commitments, and you should not expect it to converge very well because it's really a very poor agent. So that's how you would do a continuous RNN implementation in Pytorch for a gym environment. Let's talk about a couple different agents and a couple different thoughts that I've had about different agents and different papers that are using RNNs inside of reinforcement learning. So I'm actually going to exit that out, and no expectation for it to converge. But you can actually expect it to do better than just a normal MLP agent. Even if you have it like on lengths of like 4 or 6, like you'd actually be surprised just for the pendulum environment, it will increase the average reward that you receive. You know, some hyperparameter tuning is necessary, using entropy or not. Those kinds of things help. And here's a separate one using torch.discrete. But the only difference that I have right here in this one is just in constructing the distribution. Instead of a normal distribution, we're just having a categorical distribution. That's the only difference. And between this one and this one, going from continuous to discrete, the only difference we have in the entire thing is just our output. Instead of it being mu sigma, it's going to be our logits for however many classes we're choosing an action from. And, you know, that's it. Just the construction of that distribution, and everything else you can expect to be essentially the same, almost identical. And the reason why I did a discrete one is to talk about the use cases for using an RNN. So I have, so this is 2Target Grid World, which is an environment I built. So what this is it's just the simple grid world that you guys have seen in previous tutorials. However, so you the observation is the agent's current position, the current position of, you know, the first goal that you want it to go to, and the current position of the second goal you want it to go to. So if you were to use a multi-layer perceptron network on this environment, so each of them is just XY, XY, XY. So you have a total observation size of 6. Like there's no Boolean flags about whether you've gone to the first observation yet or not. So an agent will actually never be able to determine. So the environment gives you a reward when you get to the first one, and then it gives you a second reward when you go to the second one. So if you wanted to learn to go to both rewards, it has to be able to know it's gone to the first one first, because if it goes directly to the second, it's not going to receive the reward. However, with such a simple observation, there's absolutely no way that it can ever know which one it has gone to yet. There's no information provided about that. However, if you were to go ahead and use an RNN agent, that hidden state is going to be monitoring things about its observation. Like, has the hidden state gone to like some values that it has determined it has gone to the first goal point yet? So then it can go to the second one. So that's like the use case for it. Like the environment is not providing enough information, and the agent has to have some type of memory or knowledge of the that is like that is not provided directly to it, that it has to learn on its own. So for such for such an environment, and you know, the real world is a lot like that. Like the real world will not tell you if you've already done certain things in order to get to like the next state of some task or job you're trying to do. You will have to know whether you've done that first thing already, and the real world isn't going to tell you you've already done these things. You have to remember these things, and know that it's a sequential process, and certain things happen in certain orders, even if it's not providing you with all that information. So you have to be able to remember. The hidden state is great for that. And much better networks like a GRU would be much better, because you could handle much longer sequences. And GRUs are inherently better. But and for those kinds of states, you're also going to want to be using entropy as well, because when I did this one, so I'm just going to actually roll through it very slow, just if you guys want to pause at any point. All this stuff will probably be uploaded to GitHub eventually. When eventually is, I don't know, eventually. So just scrolling through that. So just so you guys know, when I ran this several times, and really wasn't learning up until I added entropy. And what I think it was going on was it was learning to reach the first goal, and then entropy would go way down, so it gained a lot of confidence. Oh yeah, I'm receiving a lot more reward now, and it would never do all the exploration that is necessary to find out that it still it could receive more reward by reaching the second goal as well. So by adding in that entropy term, it really helped it out. And I misdefined entropy in another tutorial where I talked about it in like the policy tutorial, and I said that entropy was the negative log probs, the sum of the negative log probs of every potential action in the distribution. But the correct definition for entropy is the negative sum of the probability for taking an action in that distribution times the log prob of that action in the distribution. So for all actions. So I'm just redefining that now. So here's what it looks like for a different environment. You guys can modify the grid world environment that we've done before to add a second goal, and try using this discrete 2-target grid world agent on it. And I'm just gonna go over just gonna scan over some code that I used in TensorFlow for reinforce, just because I used a sequential model for it, and I used GRU because it was super easy in TensorFlow, and I also did it on 2-target grid world, and it was able to solve it in 2-target grid world. So actually the reinforce agent does better than the A2C agent currently, because this one uses basic RNN, this one uses GRU, but obviously it takes a long time to train. But everything is the same for our reinforce agent except just the training loop. So I'm actually just gonna skip over this now. You guys can look at the code when it gets uploaded to GitHub. But yeah, this one also, it takes so just the definition of the model is essentially just different. So it takes the input, and it takes input size of 6, and instead of defining it a linear RNN layer, we're defining it as a GRU, which is technically a stack of layers, and we'll go over what a GRU is in just a minute. And the output is the number of actions, and this is a discrete agent because of what I talked about continuous agents in Pytorch, in TensorFlow, because this is a TensorFlow implementation. And this will all be uploaded in just a bit. So I'm going to go ahead and minimize that right now. Okay. And the actual environment for 2-target grid world also will end up on GitHub with everything else, but it's just not yet. I'm kind of taking my time. Anyways, so you guys saw where I copied the basic RNN agent from. So this is in Pytorch text. However, if you want to have like a more advanced agent, you can go ahead and go in NLP from scratch, translation with a sequence-to-sequence network and attention. And over here, the network that they used is down here, definition of the layer. They're going over all the basics, but you can see they used a GRU inside of it, or you could use GRU or GRU cell depending on the implementation and how you want your setup to look in general. But it would be better to use GRU or GRU cell. And the same thing. And this implementation that we did, you can, for discrete, you can copy this exact code and do it in Pytorch. So I'm not in Pytorch, in TensorFlow. So if you want to do the discrete version in TensorFlow, pretty much everything is the same. You guys know how to define models in TensorFlow. You can define the most basic TensorFlow RNN agent and run it, and you'll get the same, it'll be the same. Okay. So okay, so more reasons why you would want to use an RNN, some type of recurrent network, whether it's a GRU, LSTM, RNN, inside of your reinforcement learning algorithm. And I talked about memory, but I'm going to talk about a slightly different use case. I'm going to go over just a quick overview of 3 papers that did use it. Okay, so make sure to check out a lot of like tutorials on RNNs. They're great, really phenomenal things. And like you can do text generation with them. There's the famous, you know, Shakespeare play, writing a Shakespeare play using an RNN. You can find that in TensorFlow with generate text with an RNN. But and that's what these two papers essentially did. So world models, it converts the state into a hidden state using a variational autoencoder, and then it uses that to, instead of predicting next layers the same way that the Shakespeare paper predicts next states, that the Shakespeare paper predicts next states, or next characters. This will predict a latent representation of the next state, and it will learn on that latent representation. So check out this paper, World Models. It came out in 2018 by David Ha and Jürgen Schmidhuber. Okay, and there's also a paper that came out more recently in 2019. Great paper, one of the best. So I think these three papers are like, you know, top of the line papers as far as like state of the art for reinforcement learning and what's going on in reinforcement learning. And this one is learning a generative model for multi-step human-object interactions from videos. And it's a great paper. And this is also very similar to the Shakespeare one and how it's predicting next states and what's going on. And they built a lot of architecture around it. But pretty much assume this is like the same thing as the Shakespeare, you know, from the unreasonable effectiveness of recurrent neural networks. So assume this is the same, but instead of predicting next states or next characters for, you know, a sequence of characters, it's predicting the positions of all of the next of. So as an observation, it will find out what objects are in the environment, and then it will, for the next state, it will predict what's the position and the state of each individual object. So each individual object has a state as well. Like, you know, a cup could be full or empty, or let's say an orange could be sliced or not sliced, or, you know, things like that, which is great stuff, amazing stuff. So these are two great papers on it. And let me talk about what I'm doing in like my spare time for like what I have no idea what I'm doing, but it follows a lot of the same ideas. Okay, and these are great papers. Check them out if you're into this stuff. Check out both of these papers and this third paper. So there's this third paper is Deep Mimic Example Guided Deep Reinforcement Learning of Physics-Based Character Skills. So what this does is it takes a normal multi-layer perceptron network, and pretty much it's able to maximize multiple objectives at the same time, and which is great. So what you can do is, like, let's say you have like a walking humanoid or like an atlas or something like that. You could tell it to walk normally or walk and like skip at the same time, or like sprint, just or to hop with its feet together. Just some examples. So it can take the same agent, and the same network can have it choose like one of 4 different actions. So the input space is actually concatenated, just like our RNN network. It's concatenated with like instead of a hidden state, it's concatenated with one hot encoded vector of which action it wants to take. So like if it's the 0th one, it's normal walk. If it's the 3rd one, it's the skip walk or whatever. Now, so that's down here in skill selector, and it just helps the network determine what action sequence to take. So it's like, oh, it wants the input is telling me that it wants me to skip, so I'm going to take actions to skip. But so for in language to language models, or, you know, actually in very many different models, there's the encoder decoder architecture. So let's right here, and we can look at translate text with sequence to sequence models, which is different than generate text with RNNs. So it encodes a sequence into like a hidden state. Where is it? So it encodes a sequence into a hidden state, and our hidden state is here, and it passes that, and forget about attention for now, and it passes that to our decoder. So we have an encoder and then decoder, and right in between is a hidden state. And so this is translating English from English. We get a hidden state of our English sentence, and we pass that to our decoder, which takes that hidden state of our English and decodes that into a French sentence. Okay. So, and as you saw in the tutorial we just went over, it needs a hidden state. However, and this is just something I'm trying in my own spare time. This is not like based on tutorials or anything. We should be also able to take something very similar to the deep mimic skill selector, but we can go ahead and take a language model and we can just encode. So for example, say our discrete agent, instead of going to the first and then to the second goal, let's say there's 5 goals, and you can say go to one of 5 different goals. So the hidden state, instead of it just being a one-hot encoded, you could say encode it so you can literally take an English sentence and say go to the first goal and run that through a language model, and you'll end up with an encoded hidden state, and you pass that to your RNN, and your RNN will be able to say, oh, I know the specific action I'm supposed to take is by going through going to the first goal. Or if you encode the sentence, go to the dog. Let's say you have a dog figurine inside of your thing or whatever, and you want it to go to that and touch the dog. So you say go touch dog or something, and that's the hidden state. It's an encoded sentence of go touch dog. It knows that whenever it gets that as its hidden state for the initial, that it's gonna the action sequence that it needs to do is to go to that dog and touch it. And obviously the hidden state is going to be updated, and it's going to change as it's performing the sequence, but they're going to be dissimilar enough, hopefully, that it's able to do multiple actions depending on these encoded initial hidden states. But that's something I'm doing right now in my own time, but it's really the equivalent of taking these very basic RNN models and turning them into decoder models. So even though they're not really decoding anything, instead of just zeroed out initial hidden state, you're just telling it perform this action, and that initial hidden state is not just zeros. It's an encoding of instructions or of the task to be completed. So that's something I'm doing in my own time. Hopefully I'll be done within a few weeks or a couple months, because I do it on spare time. I'm an Uber driver right now, trying to get employment, so I'm doing this tutorial series. So when I have time, I'll be working on it. But hopefully, if you guys want to work on that, let me know how it goes, because I have trouble sometimes with it, and just setting it up, because it's setting up the environment. I'm actually creating different environments for it, just to see if it can work on different environments, instead of having one environment with a very complex reward that it understands what goal it's supposed to be going to. So like all that stuff is very time consuming, but everything will come out eventually. Those are just some ideas of like where things might be going, instead of just these very like static MLP networks. We might be using RNN networks to do like multitask objectives, and things like understanding and interpretability. Well, that's not exactly the terms that I should be using, but the agents will be better informed in what we want them to do, and they're taking user input as well as just looking at the environment and just. Anyways, I hope this was helpful for you guys. That was just me ranting a little bit at the end. Check out these papers. They're great papers of use of RNNs inside of paper in reinforcement learning. This one is not of RNNs in reinforcement learning. It was me talking about what I'm doing in my own time, which is just multi-skill integration, but using an RNN network. And it should be very similar to other decoder networks. Anyways, I'm going to go ahead. I've been talking for way too long. You guys all have a nice one. I hope this was helpful for you guys to some extent. I've been recording for way too long. Like, comment, subscribe. Let me know what I could do better. Things you saw that I did wrong in these videos. How I can help you out. And you know, new videos are going to be coming out, and they're not going to be on reinforcement learning anymore. I'm just going to do basic web development stuff. I want to push out another like 5 or 10 videos of just old projects I've done. So as I read through them and re-understand them, I'm just going to redo a couple tutorials. Okay, thank you, have a nice day, and hope you all are well.